All right, good afternoon. Today we are going to be talking about materials. This should be mostly a review, but I'm going to hopefully not just review, but kind of give you a higher level view and kind of hopefully bring some of the stuff that you might have heard before back into view for you, and also talk about how do we select materials, and hopefully I'll help you to kind of see materials from a high level view. So that's the goal, is for us to have a high level view of engineering materials. We'll talk about just real briefly creep and temperature. We'll talk about the modulus of rigidity, which corresponds to shear stresses. We will talk about the impact resistance and material resilience. That has to do with areas underneath the stress strain curve. We'll just briefly introduce fatigue strength and endure limits, the concepts, because we're going to talk about these things a lot later. We'll talk about fracture toughness. We'll also talk more about that. It's not the same thing as toughness. Then we'll talk about hardness tests, their relationship to material strength, and how do we interpret hardness tests and convert them. I'll show you a table to go from one to the other. And we'll talk about some common heat treatment processes that are used for steels, which is used ubiquitously in engineering design. We're not going to get into coatings and surface treatments, but I encourage you to read that chapter on your own. We will touch on that later when we talk about surface failure. And then we'll talk about some of the common properties, and then give a very high level view of how to select materials. So we've devoted one class to this subject of materials, and hopefully it will serve as a good review. So you'll probably remember what strain is. It's the change in length over length of some object under some load. Here we have an axial load. We have a change in length, which we often call delta here, and the strain is defined as that delta L over L. It's a dimensionless unit that we call strain. We also have shear strain as well, where we have this deflection due to a shear or transverse load, and we get this deflection angle theta. If the angle is really small, sometimes we can approximate the shear strain just by the angle, because if we're trying to find this angle, which is the tangent of theta, if we look at the Taylor series expansion for these terms, for small angle approximations, the sine of theta is about almost theta, the cosine of theta is approximately 1. And so this is our shear strain. Okay, is defined as this delta in displacement over the height of that material. Okay, and it shows up if we're looking at our shear equations. Just a brief recap, the stress is the force over the area, the strain is the change in length over the length. So if we have a load here, that's the load over the area, we get the strain delta over L. If we double the load and double the area, we still get the same delta over L. If we have the same load, but we have twice the length, then we're going to get twice the deflection, and we'll still get delta L over L, because over that deflection we'll get twice the deflection over twice the length, so we have the same strain. So these are just some brief review concepts. Hopefully you've pretty much committed this to memory already, but this is our stress strain diagram for a ductile material. We have the different regions here. We have the elastic region, where the behavior between the applied stress and the strain is linear. We use this slope here for defining Young's modulus. Elastic behavior is when the material is in this region, so any loading and unloading is all within the elastic region. If we go to the proportional limit, that's where the stress is no longer directly proportional to the strain. We have this area where this graph now becomes nonlinear, and we go all the way up into our yield stress. Okay, that's the elastic limit or plastic limit and elastic limit are sometimes the same, but that's where at the elastic limit here, that's where we define our yield stress, and that's when any additional load will cause a permanent deformation of the material, or plastic deformation, or yielding. So all the way from here to here, this is our plastic behavior. It's also where the material becomes harder, and hardening means that we have to apply more stress to get the same to get any additional strain in the material. And so in that case, it's a harder material. So we come all the way up here to this ultimate stress. That's defined as sort of the peak of the stress strain diagram. That's for the engineering stress strain diagram. It's a little bit different from our true engineering stress strain diagram, which we would get if we accounted for the change in area during the tests, but we use this value here for the ultimate stress. Beyond this point, we get necking and then ultimately fracture. Okay. So in the book, we use this notation SY instead of sigma Y for yield stress. We use SUT in the book for the ultimate tensile stress, and we use SYS for the yield stress, or SUS for the ultimate shear stress. So ductile material can endure large strains before failure. That's a very good property for a lot of machine design applications. The yield strength for some materials, such as aluminum and higher carbon steels, don't have a very well defined yield limit, or where we get this peak and then some lower values. And so instead, the 0.002 strain, or 2000 microstrain, or a 0.02% offset is used for some material. Okay, that's where they will define the yield stress. This is a low carbon steel. This is an annealed high carbon steel. Okay, and you can see the different shapes, and that there's not a super well defined yield stress here. So they take the average slope to some value, and then they just do a 2% offset and then find that intersection and define that as a yield stress. This is an example of a couple other materials. This is, again, low carbon steel. In this case, we have very high strain before failure. And this is the yield stress here is defined as 0.0012, which you see is about the 0.02% of this value for the failure. In this case, this is an aluminum alloy, where we don't have necessarily a well-defined yield point. However, we take the strain at failure, multiply it by the 0.02%, and we can define this value of yield stress. The main takeaway here is that I want you to see is that these materials will behave differently, and so from a design perspective, you just kind of, if those features of that material are important, and you need to kind of know exactly where that yield stress is, or that yield behavior, then you just kind of have to take a look at this and understand really that these yield points are just defined differently for different materials. Okay. Brittle materials typically have less than 5% elongation at failure. They also don't have a very clearly defined yield point, and so an offset line is used in this case as well, and it's usually taken as the average slope, and then you just take the average slope and then you offset it by some value. And obviously for a brittle material, the yield stress is close to the ultimate tensile stress, but you really shouldn't consider brittle materials as materials that yield. So just make sure that you're keeping these things in mind. Now, what's fascinating is that even if we alloy or heat treat different steels, that the Young's modulus stays the same. If we take different steels that have different carbon percentages, we can create stronger alloys, stronger steels, as you can see here. But again, that slope for the Young's modulus doesn't change. Okay, so that's the point here, is that even if you do some material processing or whatever, you can expect that the stiffness, or the Young's modulus, or the modulus of elasticity, is going to remain the same. Ductile materials are very good design materials in the view that when they yield, it allows the machine to have some give to it, and then it actually will get harder. So it's a strain hardening effect. So if you look here, this is a stress strain diagram for mild steel. So if you see the yield stress, it actually takes less stress for that machine, or that structural component, to continue to deform up to some value. And then it takes a lot more stress to get it to continue to deform. And so this, compared to a brittle material, these dynamics right here that allow your machine component to deform and get harder to deform after it's been deformed, where you're in this plastic region and you have this strain hardening effect, can prevent your machine from, like, completely coming apart. Now it will, can still fail, but it can fail in a way that you can predict and have some control over. Automotive sheet metal bodies are made out of ductile steel for this very reason. A lot of like shaft components and things like that are intended to, if their stress is exceeded, completely deform. Gives you a softer place to land, I guess, versus a brittle material in failure. Okay. Some materials exhibit nonlinear stress strain. This is just a stress strain diagram for rubber. So you have materials that are not not isotropic. So they have different material properties in different directions. They're not homogeneous. And so again, the material properties will differ in different directions. So this is just an example of rubber. Some materials are designed really for use only in compression, such as concrete. Okay, so, or gray cast iron. This is a stress strain diagram for that. So you can see in the tensile side it's low, and here in the compressive side we can have significantly 6 times or so higher values. Another thing to keep in mind is that steel loses its strength significantly when heated. That's why if you look at structural members for buildings, you'll often see them coated with some form of thermal protection, just to make sure that the strength of material is preserved in the event of a fire. Okay. Polymers, plastics, they have nonlinear stress strain diagrams, and they're highly temperature dependent. They're also highly susceptible to creep. Okay, so this just is a little bit, this is just a diagram showing for methacrylate. So it's going to be similar to PMMA. Then you get these different behaviors at different temperatures for the stress strain diagrams. Okay. So, creep and temperature. So creep is the phenomenon that material continues to deform under a static load. All materials will deform under the load, giving the right environmental conditions. For structural components and steels, this is especially true at elevated temperatures. So when we have a constant stress, which can be significantly lower than the yield stress, then the material can start to move. Okay, and we call this the dynamics of this creep. This is typically low melt temperatures that are susceptible to this more. Okay, so your plastics and polymers, they're going to be more susceptible to it. And so this should say that a machine designer must design against creep. Also, you have to design against fatigue, but you have to kind of design. If you have a higher temperature application, you just kind of need to be aware that creep can creep up on you, and it's something that you need to remember and be aware of. And hopefully this is something that you've covered before. This is just a reminder. Again, especially important for high temperature applications. If you have very cold applications, this is also very important, not for creep, but because it can change the material property. The material can behave as a brittle material. So you can get a very different failure mechanism if temperatures become extremely cold. Okay, so the point is that things like creep and temperature effects are important, and if you're doing design, you always got to investigate the material in all conditions that you expect, or even conditions that you might not expect in your design. In fact, automobile manufacturers, when they are launching a new vehicle, they have different environments that they'll test them, which are Arctic environments, desert environments, and then city environments. And then they try to really put the vehicle through the tests and try to find those points of failure that they may not have expected, because the cost of discovering something that you overlooked later in the product development process can be extremely expensive. The best source for you to get information about a material is actually from the material supplier itself. And for well-known materials, there's a lot of information in handbooks that you can take a look at, like Mark's, the Machinery Use Handbook, etc. Typically, when you're buying materials, there's somebody at that company who's an applications engineer, and it's really their job to help you make sure you're selecting the right material for the right application. And there's these people are a lot of help. I've spent many hours on the phone talking to application engineers to understand their products better. You don't have to go and do all of the background research and theory for a material when the company has already done that for you. You really just need to talk to the right person or get the right publication and make sure you understand it. Okay. So that was dealing with axial stress strain diagram. It's where we get a lot of our material data from. We also sometimes need to understand what our ultimate shear stress is, which is our SUS variable. So the shear stress that develops in a material such as this, subject to an applied torque here, is can be related to GR theta over L, where G is our shear modulus, kind of like the Young's modulus. It's defined here actually in terms of the Young's modulus and the Poisson's ratio, which is the ratio of lateral to longitudinal strain. The Poisson's ratio for different materials is given here. For these metals, it's about 0.3. And so if you use 0.3 in your initial calculations, and you know that is not perfectly accurate, I mean, you're going to be pretty close here. Okay. So you take your shear modulus times your radius times the angular twist in radians times the gauge length, and that's the amount of shear stress that's developed in the material. And then if we want to understand the ultimate shear stress, we can take the shear stress T, which is the applied torque at failure, times the radius over the polar mass moment of inertia. So shear stress data is not always supplied by manufacturers, ultimate shear stress data. And so what a good estimate of the ultimate shear strength for materials is to take the ultimate tensile strength data and use 80% of that value. For other ductile materials, you can use 75% of the ultimate tensile strength. If you want to find the shear yield strength, you can take about 57% or 58% of the yield stress from the axial stress strain test data. Now, we will derive this. In fact, this is controlled by or described by the failure criteria of materials, and we'll go through and we'll spend some time talking about this in more general, but this number actually comes from specific theory, and actually it's pretty fascinating that it works out. But for now, the point is that our ultimate shear strength and our yield shear strength can be approximated from the tensile test data for steels and other ductile materials with a good ballpark number. Okay. Now, obviously, in your design, if you're designing all the way to your strength limits, then you're going to have to do a lot more work to make sure that your design is safe. If you're designing far away from your strength limits, then values like these can kind of help you get started and go through the design and start to define geometries and shapes, things like that. And you can have a higher degree of confidence that you're going to be okay. Okay. When we talk about materials, there's a ductile material will also have their energy, their modulus of resistance and modulus of toughness. And these are measures of impact resistance. And so really what it is, it's a measure of, how much energy can this material handle and store. And the resilience and toughness, like I said, is a measure of its impact resistance. This is your modulus of resilience. It's sort of like how much energy can you take in the elastic region. Modulus of toughness is like, hey, how much energy can you take and not die? So we can define these values from the stress strain data. What we really care about here is this modulus of resistance, which is basically this area, which is half the plastic limit stress times the strain at the plastic limit. It's just this triangle right here, like this square, half of that, right? So we take this guy, and then we can approximate that with our yield stress here. So SY squared over 2 times Young's modulus. And this value here is, it is a way of comparing, maybe one material to another material, if you expect that material might be subject to some impact loading or whatever. Materials that have a higher value of UR will have a better ability to absorb energy and recover. And then materials that need to absorb a lot of energy, you can look at it in terms of their modulus of toughness, which is just the area under this entire curve. And it can be approximated in a similar way by looking at the average of SY over ST over 2. And we actually have to include here the strain. Okay, so I don't see that I included that. Okay, so I'm going to fix that right here. So really what we have to do is also include the strain. And this is the strain at failure. So then that is correct. Sorry about that. And that is a measure of the amount of energy the material can take before failure. And this is an approximation, just so we can kind of compare one material to another. Now, when we talk about materials, one way to look at them is as even and uneven materials. And materials will typically fail either in a brittle or ductile manner, but even ductile materials subjected to fatigue loading can fail in a brittle manner, and we'll talk a lot more about that throughout the semester. But even materials, they behave similarly in both compression and tension. Okay, so this is going to be typically, they tend to be ductile if they're even materials. Uneven materials behave differently in compression and tension, and usually, they can withstand higher compressive forces. So you can think about your cast materials, your ceramics, your cast irons, things like that. So we can just use a standard test that we have to find the failure modes. And most materials most ductile materials are even materials, and so they have the same, they can have the same failure mode in both tension and compression. Okay, and so these are your Moore's circles, and you had Moore's circle in your materials class, but this is your stress axis here. Your principal stress axis, and then this is your normal stress, and this is your shear stress. And if you go to a certain principal stress here and get failure, usually it's going to fail actually here at this max shear. So this is your failure line. Over here, these define your failure envelopes. So if you basically take your tensile test failure stress, and then you take your compressive stress compression test failure stress, and you draw your circles for those stress conditions at failure for your tensile and your compressive tests, and then you just connect the failure lines here and here. This defines a failure envelope. Similarly here in our tensile test, if this is the stress that caused failure, then this was the shear stress present. And a compression test, if this is the compression that caused failure, then this was the state of shear stress at that time. So these are our shear failure envelopes here and here. So typically, these ductile materials, even in a tensile test, are going to fail in shear. And the shear stress is less. It's less than the normal stresses or the principal stresses in that material. Okay, so the shear strength for even materials is usually less than the tensile strength that's shown here, compared to uneven materials where the shear strength is between the compressive and tensile strength. Okay, so it's kind of in between here. So these materials tend to be brittle, such as cast steel, aluminum, cinders, metals, and ceramics. When we look at that, take a little bit closer look at the conditions. So this would be our stress strain test here. This is your Moore's circle. You have yours, and we'll talk more about Moore's circle and review that later, but hopefully this is not totally new for you, or you haven't forgotten everything. So if we apply this axial stress here, okay, and then we get failure, we actually have the state of shear stress here, and we know that because of how Moore's circles allows us to resolve principal stresses. Okay, now in the Moore's circle, we know that this point here to this point is at 90 degrees, but we know that it's actually twice the angle in real life. So this 90 degrees is actually a 45-degree plane, and you can see that in the failure modes. When you have pure torsion, you have this applied shear stress. Notice this deep red line, we're applying shear. Over here, we are applying axial load. And at failure, principal stress is the same as the shear stress, okay? So because you're along this shear axis, the principal stresses, sigma 1, sigma 3 in this case, sigma 2 is 0, are the same, okay, as the magnitude of the shear stress, because it's more circle, okay, and that's the radius. The radius is the same here as it is here, so those are the same. Okay, over here in more circles, the principal stress is the same as the diameter, but the shear is the same as the radius. Okay, so it's half that value, and at failure, the shear stress is half the stress of the principal stresses. All right, but let's look at some pictures. Okay. So if we look at this axial load here, which is this case, we apply it. If we have mild steel, we see that this mild steel fails at about a 45-degree angle on that shear plane. It fails due to shear stress for the brittle material. It actually fails due to the principal stress. If we look at the compression for the brittle material in the compressive test, it actually fails in shear in this case. We saw that the failure mode was between the shear and principal stresses, and for tension it fails in the principal mode, and then in compression it fails in the shear mode. For bending here causes the bending stress, which is similar to the axial load, and it causes failure like this. For the ductile material, well, we just defined failure as it bent out of shape. And then if we look at torsion, in this case where we have the applied shear, okay, so the principal stresses are equal to the shear stresses, the failure mode for ductile material is actually in the normal plane. And you see these are opposite, okay, for the ductile material. When you apply the axial load, you get failure in the shear plane. When you apply a shear load, you get failure in the principal plane. Versus a brittle material, when you apply that torsion, that shear stress, you actually get a failure mode in that shear direction. Okay, all right. So we're going to pause here for this first half of the lecture, and then we'll come back with some more information about material properties.